Now, in this lecture, we will find the area of a circle. In the drawing, we have a circle, and inside the circle, we have a shape. Angle ADC of this shape equals to 90 degrees, and also angle BCD also equals to 90 degrees. And we know that side AD of this shape equals to 4 units, while side DC of the shape equals to 6 units, and side BC of this shape equals to 8 units, and we want to find out the area of this circle. Okay, first of all, we will define the theorem of one-sided angles. What are one-sided angles? If we have two lines, line A and line B, this is line A, and this is line B. And we have third line, line C, that intersects with lines A and B. We have line C, line C intersects with line A at this point, while line C intersects with line B at this point. Then angles alpha and beta are defined as interior one-sided angles. Okay, so I will write it down. Angles alpha and beta are interior one-sided angles. Okay, angles alpha and beta are defined as interior one-sided angles. First of all, why angles alpha and beta are defined as one-sided angles? The answer to this question is because of the fact that they are located on the same side of line C. They are defined as one-sided angles. Both of those angles, alpha and beta, are located on the left side of line C. So in relation to line C, angles alpha and beta are located in the left side of line C. For that reason, they are defined as one-sided angles. Both of those two angles located at the same side in relation to angle alpha. Both of them are located on the left side of line C. For that reason, they are defined as one-sided angles, and they are also interior angles, because both of those two angles, alpha and beta, are inside the structure of lines. We have structure of lines A, C, and B. The structure of lines A, C, and B is this structure, and they are located inside this structure. So for that reason, angles alpha and beta are defined as interior angles. So again, they are defined as one-sided angles because they both located on the same side of line C. They are both located on the left side of line C. In relation to line C, they are located on the left side of line C, and they are interior angles. Alpha and beta are defined as interior angles because they are located inside the structure of lines A, C, and B. They are located inside this structure of lines A, C, and B, and therefore they are defined as interior angles. Okay, so those two angles are defined as interior one-sided angles, and we have also the other type that are defined as exterior one-sided angles. So actually, if we have two lines, line A and line B, this is line A, and this is line B. And we have line C that intersects those two lines. So actually line C intersects line A at this point, and while line C intersects line B at this point. Actually, angles alpha and beta are defined as exterior one-sided angles. I write it down. Angles alpha and beta are defined as exterior one-sided angles. Okay, angles alpha and beta those two angles are defined as exterior one-sided angles. Okay? Why they are exterior angles? Because they are located outside of this structure. They are located outside of the structure of lines A, C, and B. Because of the fact that they are located outside the structure of lines A, C, and B, they are defined as exterior angles, and they are one-sided angles because they are located on the same side of line C. They are both located on the left side of line C. Okay, so those two angles are defined as exterior one-sided angles. Okay, and actually we have a rule. I will call it rule number 1 for one-sided angles. Rule number 1 states that if the sum of the two one-sided angles and it doesn't matter at all if they are interior angles or exterior one-sided angles, the same rule applies to both of them. So I write it here, one-sided, they can be interior or exterior. So if the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B. So I will read rule number 1 again. Rule number 1 states that if the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B. And it doesn't matter at all if they are one-sided internal angles or one-sided external angles or interior angles or one-sided exterior angles. The rule applies to both of them. If the sum of them equals to 180 degrees, whether they are interior or exterior one-sided angles, then line A is parallel to line B. So actually here if the sum of those two one-sided interior angles equals to 180 degrees if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Again, if the sum of those two angles, one-sided interior angles, equals to 180 degrees, that is to say if alpha plus beta equals to 180 degrees, then according to rule number 1, line A is parallel to line B, according to rule number 1. Okay, if the sum of those two angles equals to 180 degrees, then line A is parallel to line B. Those are one-sided interior angles, and the same rule applies to one-sided external angles. If alpha plus beta equals to 180 degrees, then line A is parallel to line B. Again, if alpha plus beta equals to 180 degrees, then line A is parallel to line B according to rule 1. And also in the one-sided interior angles, if alpha plus beta equals to 180 degrees, then line A is parallel to line B according to rule number 1. Okay, so actually we can implement rule number 1 in our circle, because we have here two one-sided internal angles. Angle ADC is one-sided internal angles. This angle that equals to 90 degrees is one-sided internal angles, and also angle BCD is one-sided internal angles, and the sum of those two angles, angle ADC plus angle BCD, equals to 180 degrees, and therefore according to rule number 1, line segment AD is parallel to line segment BC. Okay, we actually can view line segment AD as line A and line segment BC as line B, and line segment DC as line C that intersects those two lines at point D and point C, and this line segment DC creates here 90 degrees, and here we have also 90 degrees, and the sum of those two interior one-sided angles equals to 180 degrees, and therefore according to rule number 1, line segment AD is parallel to line segment BC. Okay, so I write it down. First of all, angles ADC, this angle, and angle BCD, this angle, are defined as one-sided interior angles. They are one-sided angles because both of those two angles are located in the right side of line segment DC. Both of those two angles are located in the right side of line segment DC. For that reason, they are defined as one-sided angles, and they are interior angles because they both located inside the structure of ADCB. Okay, they are located inside the structure of ADCB, inside the shape ADCB. Therefore, they are also defined as interior angles. So, those two one-sided interior angles, the sum of those two angles equals to 180 degrees. And the sum of those one-sided interior angles equals to 180 degrees, because it is 90 degrees plus 90 degrees is 180 degrees. Therefore, according to rule number 1, line segment AD is parallel to line segment BC. So I will read again the things that I wrote. Angles ADC and BCD, those two angles, this angle and this angle, are defined as one-sided interior angles. Again, they are one-sided because both of those two angles are located in the right side of line segment DC, and they are interior angles because those two angles are inside the shape ADCB. So they are defined as one-sided interior angles, and the sum of those two one-sided interior angles equals to 180 degrees, because it is the sum of those two angles are ADC is 90 degrees plus BCD is also 90 degrees, so 90 degrees plus 90 degrees equals to 180 degrees. So therefore, according to rule number 1, AD is parallel to BC. according to rule number 1, it states that if the sum of the two one-sided angles, no matter if they are interior or exterior angles, equals to 180 degrees, then line A is parallel to line B. So, according to rule number 1, because of the fact that the sum of those two one-sided interior angles equals to 180 degrees, therefore AD is parallel to BC. Okay? Okay, so we proved that AD is parallel to BC, and in the next step we will connect together points A and C by a straight line. And we will also connect together points D and B by a straight line. Okay, so we connected together points A and C by a straight line, and also points D and B by a straight line. And we will call to the point of intersection between line segments AC and DB O. Okay, point O is the point of intersection between line segments AC and DB. Okay. Then we actually will focus on two triangles, triangle BOC and triangle AOD. Okay, we will focus on the green triangle BOC. And we'll also focus on the green small triangle AOD. We'll actually prove that three angles of the big green triangle are equal to three angles to the small green triangle, and therefore those two triangles are similar. First of all, angle AOD, this angle equals to angle BOC, these angles. So actually those two angles are equal to each other because of the fact that they are vertex angles, and we have a rule number 2 that states that vertex angles are equal to each other. So first of all, I will explain you what are vertex angles. Okay, so actually when two lines are intersecting each other, for example line A intersects with line B, at this point, this is the point of intersection between lines A and B. Actually, at the point of the intersection between them, they create 4 angles. 1, 2, 3, and 4. So I will name all names for these angles. This angle is angle 1, while this angle is angle 2. This angle is angle 3, and this angle is angle 4. Okay, so those 2 angles are intersecting at this point, and at this point they created 4 angles, angle 1, angle 2, angle 3, and angle 4. Actually, we have here 2 pairs of vertex angles. The first pair of vertex angles are 1 and 3. So angles 1 and 3 are defined as vertex angles. Those 2 angles are defined as vertex angles. Angles 1 and 3 are defined as vertex angles. And they are equal to each other according to rule number 2 that I will write it down in the next step. And angle 1 equals to angle 3, according to rule number 2. So I read the things that I wrote. Angles 1 and 3 are defined as vertex angles, and according to rule number 2, they are equal to each other. So those 2 angles are defined as vertex angles, and according to rule number 2, they are equal to each other. So those are the first pair of angles that are defined as vertex angles that are equal to each other according to rule number 2. And the second pair of vertex angles are angles 2 and 4, and they are equal to each other according to rule number 2. So I'll write it down. Angles 2 and 4 are also defined as vertex angles. And they are equal to each other according to rule number 2. So I read again the things that I wrote. Angles 2 and 4 are also defined as vertex angles, and according to rule number 2 they are equal to each other. So those two angles in the red color, 2 and 4, are also defined as vertex angles, and according to rule number 2 they are equal to each other, that is to say angle 2 equals to angle 4. So now I will write down rule number 2. Rule number 2 states that vertex angles are equal to each other. So I will read again rule number 2. Rule number 2 states that vertex angles are equal to each other. Okay, you can see in the drawing that we have two vertex angles. The first pair of vertex angles are 1 and 3, and according to rule number 2 they are equal to each other, and the second pair of vertex angles are 2 and 4, and according to rule number 2 they are also equal to each other. So now I will draw them separately in order to clarify it more. So actually the first pair of angles alpha and beta are vertex angles, and according to rule number 2 they are equal to each other. So the first pair of angles are those two angles, angles alpha and beta. They are defined as vertex angles, and according to rule number 2 they are equal to each other, that is to say alpha equals to beta. And the second pair of angles will be those two angles, so I will draw it again. So actually those are the second pair of angles. Alpha and beta are also defined as vertex angles, and according to rule number 2 they are equal to each other. Again, those are the first pairs of vertex angles that are equal to each other, and those are the second pairs of vertex angles that are also equal to each other. Okay, so actually again we implemented rule number 2 in our circle because those two angles are vertex angles, and according to rule number 2 they are equal to each other. Okay, so I write it down. Angle AOD equals to angle BOC. Those two angles are equal to each other. Angle AOD equals to angle BOC because they are vertex angles, and according to rule number 2 they are equal to each other. So okay, so I wrote it down. Angle AOD equals to angle BOC because they are vertex angles, and according to rule number 2 vertex angles are equal to each other. And actually in the next step I will explain you what are alternating angles. Okay, so actually if we have two lines, line A and line B, this is line A and this is line B, and we have also line C that intersects those two lines. Line C intersects those two lines. This is the point of intersection between line C and line A, while this is the point of intersection between line C and line B. Line C in the red color and line B. Okay, actually angles alpha and beta are defined as interior alternating angles. Okay, those two angles are defined as interior alternating angles. So I write it down. Alpha and beta are defined as interior alternating angles. Okay, those two angles alpha and beta are defined as interior alternating angles. And again, why? First of all, why they are alternating angles? Why they are defined as alternating angles? They are defined as alternating angles because they are located in different sides in relation to line C. Those two angles alpha and beta are located in different sides of line C, while angle alpha is located in the left side of line C, angle beta is located in the right side of line C. For that reason, those two angles that are located in different sides of line C are defined as alternating angles. Okay, and they are also defined as interior angles because they are actually inside the structure of lines A, C, and B. We have the structure of lines A, C, and B, and they are inside this structure. For that reason, they are defined as interior angles. So they are defined as interior alternating angles. Okay. And we also have the second type of angles that are defined as exterior alternating angles. So actually, if we have two lines, line A, this is line A, and this is line B. And we have line C that intersects those two lines. So line C intersects those two lines. Line C intersects with line A at this point, while line C intersects with line B at this point. Actually, angles alpha and beta are defined as exterior alternating angles. Those two angles, alpha and beta, are defined as exterior alternating angles. So I'll write it down. Angles alpha and beta are defined as exterior alternating angles. Okay, angles alpha and beta are defined as exterior alternating angles. Again, why they are alternating angles? Because they are located in different sides of line C. In relation to line C, they are located at different sides of line C, while angle alpha is located in the left side of line C. Angle beta is located on the right side of line C. For that reason, they are defined as alternating angles. And why are they defined as exterior angles? Because both two angles are located outside the structure of lines B, C, and A. Those two angles, beta and alpha, are located outside of the structure of lines B, C, and A. They are located outside of this structure. For that reason, they are defined as exterior angles. Okay, so those two angles are interior alternating angles, while those two angles are defined as exterior alternating angles. And we actually have rule number 3 for alternating angles. Okay, rule number 3 states alternating angles between parallel lines are equal to each other. So I will read rule number 3 again. Rule number 3 states that alternating angles between parallel lines are equal to each other. So actually here in this drawing, if line A is parallel to line B, if line A is parallel to line B, then according to rule number 3, angle alpha equals to angle beta. Okay, according to rule number 3. Again, if line A is parallel to line B, then according to rule number 3, alpha equals to beta. Okay, only if line A is parallel to line B, only then we can deduce that according to rule number 3, angle alpha equals to angle beta. Okay? And it doesn't matter if we relate to alternating interior angles as in this case, or relate to exterior alternating angles. The same rule applies also to the exterior alternating angles. Also here, if line A is parallel to line B, if line A is parallel to line B, then according to rule number 3, alpha equals to beta. Okay, according to rule number 3, angle alpha equals to angle beta. So it doesn't matter at all if we are talking about exterior alternating angles or interior alternating angles. The same rule applies to both of them. In the interior alternating angles, if line A is parallel to line B, alpha equals to beta, and also in the exterior alternating angles, if line A is parallel to line B, then alpha equals to beta, according to rule number 3. Okay, so we actually can implement rule number 3 in our circle. Actually, we have angle DAO, this angle that is in relation to angle BCO. Those two angles are defined as alternating angles because they are located on different sides in relation to line segment AC. Okay, those are alternating angles, those two angles, and they are located between parallel line segments. We have already proved that line segment BC is parallel to line segment AD. AD is parallel to BC, and there are two alternating angles. So according to rule number 3, alternating angles, those two angles between parallel lines, AD is parallel to BC, are equal to each other. Therefore, angle DAO equals to angle BCO. Okay? So, I will write down the things that we have found until now. First of all, we focus on the two green triangles, triangle BOC and triangle AOD. So, on these two plane triangles, angle AOD equals to angle BOC. Those two angles are equal to each other because they are vertex angles, and according to rule number 2, they are equal to each other. So I write it down. Vertex angles are equal to each other. Okay, angle in triangle BOC and triangle AOC, the two green triangles, angle AOD equals to angle BOC because they are defined as vertex angles, and according to rule number 2, vertex angles are equal to each other. Okay, so those two angles are equal to each other. And also we have already found out that angle DAO equals to angle BCO. Angle DAO equals to angle BCO. According, because they are alternating angles, and according to rule number 3, alternating angles between parallel lines, AD is parallel to BC, are equal to each other. So those two alternating angles are equal to each other because they are located between parallel line segments. AD is parallel to BC. For that reason, this angle equals to this angle according to rule number 3. So angle DAO equals to angle BCO because those two angles are defined as alternating angles, and they are located between parallel line segments. AD is parallel to BC, so according to rule number 3, they are equal to each other. Okay, and also angle ADO, this angle, and angle CBO, this angle, those two angles are defined as alternating angles because they are on two different sides of line segment BC. They are located on two different sides of line segment BD, and they are also located between the parallel line segments AD and BC. And according to rule number 3, alternating angles between parallel lines are equal to each other. Okay, so actually we can write down that angle ADO equals to angle CBO because they are alternating angles and they are located between parallel lines. Line segment AD is parallel to line segment TC, and according to rule number 3, alternating angles between parallel lines are equal to each other. Okay? For that reason, angle ADO equals to angle CBO. So angle ADO equals to angle CBO. Those two angles are equal to each other because they are alternating angles. They are located on different sides of line segment BD, and they are between parallel line segments. Line segment AD is parallel to line segment BC, and according to rule number 3, alternating angles between parallel lines are equal to each other. For that reason, those two angles are equal to each other. So angle ADO equals to angle CBO because they are alternating angles, and according to rule number 3, alternating angles between parallel lines are equal to each other. So we actually proved in relation to these two triangles, green triangles, that those two angles are equal to each other, and also those two angles are equal to each other, and also those two angles are equal to each other. So we actually proved that three angles in this big green triangle are equal to three angles in this small green triangle. So actually, according to angle, A is abbreviation for angle. According to angle, the big triangle BOC is similar to the small triangle AOD. Okay? So those two green triangles are similar to each other. According to angle, triangle BOC is similar to triangle AOD. So actually, when you prove that two triangles are similar to each other, then you have special relationship between their sides. I'll give you an example of other two triangles that are similar to each other. So if the big triangle ABC is similar to the small triangle DEF, that is to say three angles of this big triangle are equal to three angles of the small triangle, then the following relationship exists between the sides of those two triangles. A, B, so this relationship exists between the sides of those two similar triangles. AB over DE equals to BC over EF equals to AC over DF. Again, AB over DE equals to BC over EF equals to AC over DF. Okay? Okay? If two triangles are similar to each other, then you have this relationship between the sides of those two triangles. This side over this side equals to this side over this side equals to this side over this side. Okay? So actually we can implement the rule of similar triangles in our circle, because we have here two green similar triangles. We have already proved that those two green triangles are similar to each other. So we can say that OB over OD equals to OC over OA equals to BC over AD. Okay, the relationship between those two similar triangles are OB over OD equals to OC over OA equals to BC over AD. Okay? So, but we know that BC, it is given us in the question that BC equals to 8 units and AD equals to 4 units. So, I can write here that BC equals to 8 units while AD equals to 4 units. Okay? So we have 8 over 4 is 2. So we got this equality. OB over OD equals to OC over OA equals to BC over OA, that equals to 2. So we actually have this equality that OB over OD equals to 2. So we can write it separately. OB over OD equals to 2. So if OB over OD equals to 2, we can multiply this equality by OD, and we will get that OB, we multiply this equality by OD, we will get that OB equals 2 times OD. Okay, OB equals 2 times OD. So actually, if OD equals to A, then OB equals 2 times OD. OB equals 2 times OD, so OB equals 2 times A. Because OB equals 2 times OD, and OD equals to A, so OB equals 2 times A. Okay, and also we have the second equality from this. We can derive the second equality from this equality. The second equality is OC over OA also equals to 2. Okay, we can derive the second equality that OC over OA equals to 2. Okay, OC over OA equals to 2. We can multiply this equality by OA. We will get that OC equals 2 times OA. OC equals 2 times OA. Okay, OC equals 2 times OA. So actually, if OA equals to B, then OC equals 2 times OA. So OC that equals to B will be equal to 2B. Okay, OC equals 2 times OA, and OA equals to B, so OC equals 2 times B. Okay, so in the next step, as you can see from the drawing, angle BCD, this angle equals to 90 degrees, so write it down. Angle BCD equals to 90 degrees. Therefore, triangle BCD is a right triangle. So we can apply the Pythagorean theorem in the right triangle BCD. This right triangle, according to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, that is to say, the square of the hypotenuse is dB squared equals to the sum of the squares of the perpendiculars equals to BC squared plus DC squared. Again, according to the Pythagorean theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, dB squared equals to BC squared plus DC squared. Okay, that is the implementation of the Pythagorean theorem in the right triangle BCD. Okay, the square of the hypotenuse is dB squared equals to the sum of the squares of the perpendiculars equals to BC squared plus DC squared. What is the value of dB? dB equals to OD plus dB equals to OD plus OB. OB plus OD is dB, but OB equals to 2 times A and OD equals to A. So ODB equals in total to 2A plus A, so dB equals to 3A. So we can substitute dB by 3A. dB squared is 3A squared, while BC equals to 8 units. So we can substitute BC by 8. So BC square is 8 square plus DC square. DC equals to 6 units. So DC square is 6 square. So in total we got that 3a square equals to 8 square plus 6 square, because dB equals to 3a, so dB square will be equal to 3a square, and BC equals to 8 units, so BC square will be equal to 8 square, and DC equals to 6 units, so we can substitute DC by 6, and DC square is 6 square. Okay, but 8 square is 64 and 6 square is 36, so I write it down. So we got that 3a square equals to 64 plus 36. 64 plus 36 equals to 100. So I will write it down. So we got that 3a square equals to 100. In the next step, we will take a root out of this equality. Actually, the root of 100 is 10, so I write it down. The root of 3a square is 3a, and the root of 100 is 10, so we got that 3a equals to 10, so we will divide this equality by 3 in order to get the value of a. A equals to 10 over 3 units we got that a equals to 10 over 3 units. So if a equals to 10 over 3 units, 2 times a will be equal to 20 over 3 units. Okay, so in total we got that a equals to 10 over 3 units, while 2 times a equals to 20 over 3 units. So we actually can write here that a equals to 10 over 3 units, while 2 times a equals to 20 over 3 units. Okay. In the next step, we actually know that angle ADC equals to 90 degrees. It is given us in the question that angle ADC equals to 90 degrees. So if angle ADC equals to 90 degrees, then triangle ADC is a right triangle. So triangle ADC is a right triangle, so we can implement the Pythagorean theorem in the right triangle ADC. According to the Pythagorean theorem, the square of the hypotenuse, that is to say AC square, the hypotenuse is AC, and the square of the hypotenuse is AC square, equals to the sum of the squares of the perpendiculars equals to AD square plus DC square. Okay, so in the right triangle ADC, we implemented the Pythagorean theorem that states that the square of the hypotenuse, that is to say AC square, equals to the sum of the squares of the perpendiculars equals to AD square plus DC square. Okay, so AC equals to AO plus OC, AO equals to B and OC equals to 2B, so B plus 2B equals to 3B, so AC equals to 3B and AC square is 3B square equals to AD square. AD equals to 4, so AD square is 4 square plus DC square. DC equals to 6, so DC square is 6 square. So in total we got that 3B square equals to 4 square plus 6 square. 4 square is 16 and 6 square is 36, so I will write it down. So we got that 3B equals to 16 plus 36. 16 plus 36 is 52, so I write it down. And here is actually 3B square. Here we have 3B square equals to 16 plus 36, and 16 plus 36 is 52, so I write it down. So we got that 3B square equals to 52. Now we will take a root out of this equality. We will get that the root of 3B square is 3B equals to the root of 52. Okay. Actually 52 equals to 13 times 4, and we can also split the root to 2 roots according to the rule that the root of A times B equals to the root of A times root B. Okay. So we got that 3B equals to 13 times 4, and we can also split the root to 2 roots according to the rule that the root of A times B equals to the root of A times root B. Okay. So we got that 3B equals to 13 times 4, and we can also split the root to 2 roots according to the rule that the root of A times B equals to the root of A times root B. So we got that 3B equals to 13 Root of 4 times root 13. The root of 4 is 2, so I write it down. So we got that 3b equals to 2 times root 13. We will divide this equality by 3 in order to get out to get the value of b. So naturally divided this equality by 3. We got that b equals to 2 over 3 times root 13. If b equals to 2 over 3 times root 13, then 2 times b will be equal to 4 over 3 times root 13. Okay, so 2 times b equals to 4 over 3 times root 13. Okay, in total we got that b equals to 2 over 3 times root 13, while 2 times b equals to 4 over 3 times root 13. Okay, so I write it here. B equals to 2 over 3 times root 13, while 2 times b equals to 4 over 3 times root 13. Okay, so we actually know all the values of all the line segments inside this circle. So I will copy this drawing here without A and B, because we have already know the values of A and B. Okay. AO equals to 2 over 3 times root 13. While OC equals to 4 over 3 times root 13. DO DO equals to 10 over 3, while OB equals to 20 over 3 units. Okay. In the next step, we will extend line segment AC until it touches the circle at point, let's say point P. So we actually extended line segment AC until it touches the circle at point P. Point P is the point of contact between the circle and chord AP. Okay, P is the point of contact between the circle and the chord AP. Okay, so we actually created new line segment CP, and in order to find out the value of line segment CP, we will implement on this circle new rule number 4. Okay, so actually according to rule number 4, if we have two chords, let's say chord AB and chord CD, that are intersecting each other at point O. Point O is the point of intersection between chords AB and CD. So if this is the reality, that we have two chords, chord AB and chord CD, that are intersecting each other at point O, then we have the following relationship between the line segments that were created due to this intersection between those two chords. The following relationship are true for the new line segments that were created. AO times OB equals to OC times OD. Again, when you have two chords that are intersecting each other, that is to say chord AB intersects with chord CD and the point of intersection is at point O, then the following equality is true, that AO times OB equals to OC times OD. Okay? When you have two chords that are intersecting each other at point O, then AO times OB equals to CO times OD. So we actually can implement, first of all, I will write down rule number 4. So actually rule number 4 states if two chords chord AB and chord DC are intersecting each other at point O, then the following equality is true. AO times OB equals to OC times OD. So I will read rule number 4 again. If two chords AB and CD are intersecting each other at point O, we have two chords, chord AB and chord CD are intersecting each other at point O. Point O is the point of intersection between those two chords. Then the following equality is true. Then the following equality is true, that AO times OB equals to CO times OD. Okay? So we actually can implement rule number 4 in our circle. Because we have chord AP, chord AP intersects with chord DB at point O. Again, chord AP intersects with chord DB at point O. O is the point of intersection between chord AP and chord DB. Okay, so I write it down. Chord AP intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DB. So, according to rule number 4, AO times OP equals to DO times OB. So, I'll read again the things that I wrote. Chord AP intersects with chord DB. Chord AP intersects with chord DB at point O. Okay, so according to rule number 4, AO times OP equals to DO times OB. Okay, again, AO times OP equals to DO times OB. Okay, so we know that AO equals to 2 over 3 times root 13, while OP equals to OC plus CP. Again, OP equals to OC plus CP. While DO equals to 10 over 3 units, and OB equals to 20 over 3 units. Okay, OB equals to 20 over 3 units. So in total we got that 10 over 3 times root 13 equals to CO plus CP, that equals to 10 over 3 times 20 over 3. What is the value of OC? The value of OC is 4 over 3 times root 13. Again, the value of line segment OC is 4 over 3 times root 13. So I write it down. So the value of CP is 4 over 3 times root 13. So we have here 10 over 3 times root 13. We actually have root 13 times root 13 is 13, and 2 times 4 is 8. So I write it down. So in total we got that again 10 over 3 times root 13 times 4 over 3 times root 13 is 8 over 3 times 13, because 10 times 4 is 8, and root 13 times root 13 equals to 13. So in total we got that we have here 8 over 3 times 13 plus 10 over 3 times CP equals to 10 over 3 times 20 over 3. We actually have in this side of the equation 3 in the denominator, and we have in the other side of the equation 3 in the denominator, so we can cancel 3 because we have 3 in both sides of the denominator. Okay. Okay, we cancel 3 in this side of the equation, and we cancel 3 in the other side of the equation. Okay. Actually, here we have 2 over 3 times root 13 times 4 over 3 times root 13. So we have in the denominator 2 times 3. So only 1 3 is cancelled. Okay, because we have in the denominator 3, and we have also 3, the second 3 here. So we have 3 times 3 in the denominator, and we cancel only 1 3, so the other 3 is left. Okay. So actually in total we got that 8 times 13 over 3 plus 2 times root 13 times CP equals to 10 over 20 over 3. 10 times 20 over 3. 8 times 13 is 104, and 10 times 20 is 200, so I write it down. So we got that 104 over 3 plus 2 times 13 times CP equals to 200 over 3. Now we'll subtract 104 over 3 from this equality. We subtracted 104 over 3 from this equality, we got the 2 times root 13 times CP equals to 203 over 200 over 3 minus 104 over 3. So 200 minus 104 is 96. So in total we got here 96 over 3. So we got that 2 times root 13 times CP equals to 96 over 3. 96 over 3 is 32, so I write it down. So we got that 2 times root 13 times CP equals to 32. We'll divide this equality by 2. So we got that root 13 times CP equals to 16. We will divide this equality by root 13 and we will get the value of CP. So we got that CP equals to 16 over root 13 units, okay? CP equals to 16 over 13 units. So I write it here. The value of line segment CP is actually 16 over root 13 units. Okay. In the next step, we will extend line segment DC until it touches the circle at point Q. So we extend that line segment DC until it touches the circle at point Q. Actually, point Q is the point of contact between the circle and chord DQ. Again, point Q is the point of contact between the circle and chord DQ. And we will do the same process again in order to find out the value of the new line segment that was created, CQ. We will implement rule number 4 in our circle. We have chord AP intersects with chord DQ at point C. Again, point C is the point of intersection between chord AP and chord DQ. Therefore, according to rule number 4, AC times CP equals to DC times CQ. So I read the things that I want. Chord AP intersects with chord DQ at point C. Okay, chord AP intersects with chord DQ at point C. Point C is the point of intersection between chord AP and chord DQ. Therefore, according to rule number 2, AC times CP equals to DC times CQ. Okay? AC equals to 2 over 3 times root 13 plus 4 over 3 times root 13. So in total AC equals to 6 over 3 times root 13. The value of CP, we've already found out the value of CP is 16 over 13 units. 16 over root 13 units, okay? The value of CP is 16 over 13, or 16 over root 13 units, while the value of DC is 6 units, and the value of CQ is missing. That is the value that we want to find out. Okay, so I will leave CQ as it is. This is the value that we want to find out, the value that is missing. So in total we got that 6 over 3 times root 13 times 16 over root 13 equals to 6 times CQ. Here 6 over 3 is 2, and we have root 13 in the numerator and we have root 13 in the denominator. So root 13 is cancelled. We have root 13 in the numerator and we have root 13 in the denominator. So root 13 is cancelled. 6 over 3 is 2. So I write it down. Again, 6 over 3 is 2, so in total we got 2 times 16, because root 13 is cancelled. Okay, so in total we got that 2 times 16 equals to 6 CQ. 2 times 16 is 32, so I write it down. So we got that 32 equals to 6 CQ. We will divide this equality by 2. We will get that 16 equals to 3 CQ. Okay, we got that 16 equals to 3 CQ. We'll divide this equality by 3 in order to get the value of CQ. CQ equals to 16 over 3 units. So we got that the value of CQ equals to 16 over 3 units. So write here that the value of 16, the value of CQ, the value of line segment CQ equals to 16 over 3 units. Okay. In the next step, we will extend line segment CB until it touches the circle at point, let's say, point R. Okay, we extended line segment BC until it touches the circle at point R. Point R is the point of contact between the circle and chord RB. Again, point R is the point of contact between the circle and chord RB. And we'll repeat the same process in order to find out the value of the new line segment RC. Okay, so actually chord RB intersects with chord DC at point C. Okay, chord RB intersects with chord DQ at point C. Point C is the point of intersection between chord RB and chord DQ. So according to rule number 4, RC times BC equals to DC times CQ. So I will read again the things that I wrote. Chord RB intersects with chord DQ at point C. Chord RB intersects with chord DQ at point C. C is the point of intersection between chord RB to chord DQ. Therefore, or so, according to rule number 4, RC times BC equals to DC times CQ. Again, RC times BC equals to DC times CQ. Okay, RC is the missing line segment, so I will leave it as it is. RC will remain as RC, while BC equals to 8 units, so I'll substitute BC by 8, equals to DC equals to 6 units, times CQ equals to 16 over 3 units. So in total we got that RC times 8 equals to 6 times 16 over 3. 6 over 3 is 2, so I write it down. So we got that RC times 8 equals to 10 times 16. 10 times 16 is 32, so I write it down. So we got that 8 times RC equals to 32. We'll divide this equality by 8 in order to find out the value of RC. (32 over 8 is 4). So we got that RC equals to 4 units. Okay, we got that RC equals to 4 units. So we can write here that RC equals to 4 units. Okay. So we actually have all the values of all the line segments inside the circle, and the only missing thing is the radius of this circle. After we will find out the radius of this circle, we will immediately know what is the area of this circle, because the area equals the area of any circle. The area of any circle equals to pi times the radius squared. Okay, so in order to find out the radius of this circle, we will implement new rule number 5. Okay, we will implement rule number 5 in this circle. According to rule number 5, or rule number 5 states that if two chords are intersecting each other at 90 degrees, if we have, for example, chord AB that intersects with chord CD, at 90 degrees. They intersect each other at 90 degrees, or at the point of intersection that can be called point O. They create 90 degrees with each other. This angle is 90 degrees, and also all the other 3 angles equal to 90 degrees. So if we have two chords, chord AB and chord CD, that are intersecting each other at 90 degrees, then the following equality is true. That 4 times r squared, when r is the radius of this circle, equals to ao squared plus bo squared plus co squared plus do squared. So I'll repeat again on rule number 5. Rule number 5 states that rule number 5 states that if we have two chords, chord AB and chord CD, that are intersecting each other at 90 degrees, they create at the point of intersection point O 90 degrees of each other, then the following equality is true. That 4 times r squared, r is the radius of this circle, equals to ao squared plus bo squared plus co squared plus do squared. Okay, so I will write down rule number 5. Rule number 5 states that if two chords are intersecting each other at 90 degrees, chord AB intersects with chord CD at 90 degrees. They create 90 degrees at the point of intersection. That is to say at point O. At 90 degrees at point O, then the following equality is true. That 4 times r squared equals to ao squared plus ao squared plus bo squared plus co squared plus do squared. So I will read rule number 5 again. Rule number 5 states that if two chords are intersecting each other at 90 degrees at point O, chord AB intersects with chord CD at 90 degrees at the point of intersection point O, they create 90 degrees with each other. All the angles at the point of intersection are equal to 90 degrees. Okay, if this is the reality, then the following equality is true. That 4 times the radius squared, 4 times the radius of this circle squared, equals to ao squared plus bo squared plus co squared plus do squared. Okay? Again, if we have two chords that are intersecting with each other at 90 degrees, then immediately we can implement rule number 5, that states that 4 times the radius of that circle squared equals to AO squared plus OB squared plus CO squared plus DO squared. Okay, so we can actually implement rule number 5 in our circle. Because we have angle BCD that equals to 90 degrees. This angle equals to 90 degrees. And chord DQ intersects with chord RB at 90 degrees. Again, chord DQ intersects with chord RB at 90 degrees. Chord DQ intersects with chord RB at 90 degrees. And the point of intersection is point C between those two chords. So, according to rule number 5, four times the radius of this circle squared equals to DC squared plus CQ squared plus RC squared plus BC squared. So I'll read again the things that I wrote. Chord DQ intersects with chord RB at 90 degrees at point C. Chord DQ intersects with chord RB at 90 degrees. They create 90 degrees at the point of intersection, point C. So we can implement here rule number 5. Rule number 5 says that 4 times the radius of this circle squared equals to DC squared plus CQ squared plus RC squared plus BC squared. Again, 4 times R squared, R is the radius of the circle, equals to DC squared plus CQ squared plus RC squared plus BC squared. Okay? And so 4 times the radius of the circle squared equals to DC squared. DC is 6, and so 6 squared is 36 plus CQ squared. CQ equals to 16 over 3, and 16 over 3 is 5/3. So 5/3 squared equals to 28.444. Plus RC squared. RC equals to 4, so 4 squared equals to 16 plus BC squared. BC equals to 8 units, so 8 squared is 64. So in total we got that 4 times the radius of the circle squared equals to 36 plus 28.444 plus 16 plus 64. 64 plus 36 is 100. 100 plus 16 is 116. And 116 plus 28.444 equals to 144.444. So I will write it down. In total we got that 4 times the radius squared equals to 144.444. Okay, so if we sum this side of the equation, the sum of this side of the equation is 144.444, all equals to 4 times the radius squared. We divide this equality by 4 and we will get the radius of this circle squared. So we get that r squared equals to 36.111. So we got that the radius of the circle squared equals to 36.111. But we know that the area of any circle equals to pi times r squared. Okay, the area of any circle equals to pi times the radius of the circle squared. But we have already know that r squared equals to 36.111, so the area of the circle will be equal to the area of the circle will be equal to pi times r squared, and r squared equals to 36.111. Okay, r squared is 36.111. So in total we got that the area of the circle equals to pi times 36.111 square units. So in total we got that the area of this circle equals to pi times 36.111 square units. So in terms of numbers, we will get that the area of the circle equals to 113.45 square units. So I will check that I'm not mistaken. I'll check the area okay, the area of this circle equals to 113.45 square units. Again, the area of this circle equals to 113.45 square units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the area of this circle, and inside the circle we have a shape, and the two angles of this shape equals to 90 degrees. This is a right angle, and also this is a right angle. Side AD of this shape that inside the circle equals to 4 units. Side DC of this shape equals to 6 units. And side BC of this shape equals to 8 units. And we want to find out the area of this circle. Okay. In order to find out the area of the circle, first of all, we must explain the term of one-sided angles. Okay. What are one-sided angles? So actually, if we have two lines, lines A and line B, and we have the third line, line C, that intersects those two lines, that is the point of intersection between line C and line A, and that is the point of intersection between line C and line B. So actually alpha and beta are defined as one-sided internal angles. They are one-sided angles because they are located on the same side of line C. They are both located on the left side of line C. For that reason, they are defined as one-sided angles, and they are interior angles because they are inside the structure of lines A, B, and C. They are inside this structure, so they are interior angles, and they are one-sided because they are in the same side of line C. They are in the both on the left side of line C. In relation to line C, they are located in the left side of line C, so they are defined as one-sided angles. Okay, so those are the one-sided interior angles, and the other type are one-sided exterior angles. Again, they are located on the left side of line C. For that reason, they are both of them located on the left side of line C. For that reason, they are defined as one-sided angles. and they are exterior angles because they are located out of the structure of lines A, B, and C. This is the structure of lines A, B, and C, and they are located outside of this structure. For that reason, they are exterior angles. Okay, and actually we have rule number 4 that states that if the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B, and it doesn't matter if they are interior angles or exterior angles. Here, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. And also here, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Okay, so we actually implemented rule number 1 in our circle because we have angle ADC, that is right angle, and also angle BCD is right angle. So there are two one-sided internal angles. Okay, you can see it. AD is line A, PC is line B, and DC is line C. And they are inside this structure, so they are one-sided internal angles, and the sum of these one-sided internal angles equals to 180 degrees because 90 degrees plus 90 degrees is 180 degrees. Therefore, according to rule number 1, AD is parallel to BC. Because of the fact that the sum of those two angles, those two one-sided internal angles, is equal to 180 degrees, because 90 degrees plus 90 degrees is 180 degrees. According to rule number 1, line segment AD is parallel to line segment BC. Okay, and in the next step we connected together lines A and C by a straight line, and we also connected together lines B and D by a straight line, and we actually created two green triangles, and we proved that those two green triangles are similar to each other because actually this angle is equal to this angle. Those are two vertex angles, and according to rule number 1, vertex angles are equal to each other. Okay. I will repeat briefly on the definition of vertex angles. If two lines are intersecting each other at this point, then they create four angles, 1, 2, 3, and 4. They create actually two pairs of vertex angles. Angles 1 and 3 are the first pair angles, and they are equal to each other according to rule number 2 that states that vertex angles are equal to each other. And also angles 2 and 4 are defined as vertex angles, and according to rule number 2 they are equal to each other. So actually we have those two angles are vertex angles. According to rule number 2, alpha equals to beta, and also those two angles are defined as vertex angles, and according to rule number 2 they are equal to each other, so alpha equals to beta. So actually implemented rule number 2 in our circle, because we have here two vertex angles, angle BOC equals to angle AOD, because they are vertex angles, and vertex angles are equal to each other. Okay? And then we define the term alternating angles. If we have two lines, line A and line B, and we have line C that intersects those two lines, this is the point of intersection between line C and line A, and this is the point of intersection between line C and line B, then they create two alternating angles, angle alpha and angle beta. Why are they are defined as alternating angles? Because they are located in different sides in relation to line C. Okay, while angle beta is located in the left side of line C, angle alpha is located in the right side of line C. So because of the fact that they are located in different sides of line C, they are defined as alternating angles, and they are also inside the structure of lines A, B and C. They are inside this structure. For that reason they are also defined as interior angles. So in total they are defined as interior alternating angles. And the second type of alternating angles are exterior alternating angles. Again, they are located in different sides of line C. For that reason they are defined as alternating angles, and they are located outside of this structure. For that reason they are defined as exterior angles. In total they are defined as exterior alternating angles. And we have rule number 3 that states that alternating angles between parallel lines are equal to each other. Those two alternating angles, okay, and if we know that line A is parallel to line B, so if A is parallel to B, then angle alpha equals to angle beta. Okay, if line A is parallel to line B, then angle alpha equals to angle beta. And also here, if line A is parallel to line B, if those two lines are parallel to each other, then angle alpha equals to angle beta. According to the rule number 3 that states that alternating angles between parallel lines are equal to each other, and it doesn't matter at all if they are exterior angles or interior alternating angles. In both sides they are equal to each other if line A is parallel to line B. Okay, so we actually implemented rule number 3 in our circle, because we have here two alternating angles. Those two angles are alternating angles because they are located on different sides of line segment AC. They are located on two different sides of line segment AC. For that reason they are defined as alternating angles. And also they are located between parallel lines, between parallel line segments. Line segment AD is parallel to line segment BC. We have already proved it according to rule number 1. So those two alternating angles are located between parallel lines, and therefore, according to rule number 3, they are equal to each other. And the same thing we can say about those two angles. Those two angles are alternating angles because they are located from different sides of line segment DB. And they are also located between parallel line segments. Line segment AD is parallel to line segment BC, so according to rule number 3, they are equal to each other. So in total we proved that those two angles are equal to each other because they are vertex angles, and according to rule number 2, they are equal to each other. And we also proved that those two angles are equal to each other according to rule number 3, that alternating angles between parallel lines are equal to each other. And we also proved that those two angles are also equal to each other according to rule number 3, that states that alternating angles between parallel lines are equal to each other. So we actually proved that three angles of this green triangle, three angles of this green big triangle are equal to three angles of this green small triangle. So we actually proved that the big green triangle is similar to the small green triangle according to the rule that angle. If you prove the three angles of one triangle are equal to three angles of the other triangles, you actually prove that those two triangles are similar to each other. So we actually proved that those two green triangles are similar to each other. And whenever you have two similar triangles, for example, if triangle ABC is similar to triangle EDF, then we have the following relationship between the sides of those two triangles. AB over DE equals to BC over EF equals to AC over DF. Okay? So we implemented this relationship between the similar green triangles. We can say that OB over OD equals to OC over OA equals to BC over AD. Okay? OB over OD equals to OC over OA equals to BC over AD. But we know that BC equals to 8 units while AD equals to 4 units. So we can write here that BC equals to 8 units and AD equals to 4 units. So actually 8 over 4 equals to 2. So we actually have the first equality that states that OB over OD equals to 2. We multiplied this equality by OD and we got that OB equals to 2 times OD. And we also have the second equality that states that OC over OA equals to 2. We multiply this equality by 2 and we got that OC equals 2 times OA. Okay, so actually we know that OB equals 2 times OD. So if OD equals to A, then OB equals 2 times A. And we know that OC equals 2 times OA. So if OA equals to B, then OC equals 2 times B. Okay? And then we have angle BCD. Angle BCD, this angle equals to 90 degrees. So if angle BCD equals to 90 degrees, then triangle BCD is a right triangle. And if triangle BCD is a right triangle, we can implement the Pythagorean theorem in this right triangle. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say B square equals to BC square plus DC square. Okay, in the right triangle BCD, the square of the hypotenuse dB square equals to BC square plus DC square. And dB equals to A plus 2A, dB equals to 3A, while we know that BC equals to 8 units and DC equals to 6 units, so the only missing variable here is A. So we put the data in the equation of the Pythagorean theorem, and we found out that A equals to 10 over 3 units, while 2A equals to 20 over 3 units. So OB equals to 20 over 3 units, and OA equals to 10 over 3 units, okay? And then we repeated on the same process. Here we know that angle ADC equals to 90 degrees because it is given us in the question that it equals to 90 degrees. So therefore triangle ADC is a right triangle, so we can implement the Pythagorean theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. Okay, AC square equals to AD square plus DC square. Okay, and again, we know that AC equals to OA plus OB, that is to say equals to B plus 2B plus 2B, B plus 2B is 3B, so AC equals to 3B, and AD equals to 4 units, and DC equals to 6 units. So the only missing variable is B. So we put the data inside the equation of the Pythagorean theorem, and we found out that the value of B is 2 over 3 times root 13 units, while the value of 2B equals to 4 over 3 times root 13 units. Okay, so we found out all the values of all the line segments inside this circle, and I copied again this drawing here, and in the next step we extended line segment AC until it touches the circle at point P. Point P is the point of contact between the circle and chord AP, and we actually created new line segment CP, and we found out the value of CP according to the fourth rule. According to the fourth rule, if we have two chords, chord AB and chord CD, that are intersecting each other at point O. Point O is the point of intersection between chord AB and chord DC. Then the following equality is true. That is to say, AO times OB equals to OC times OD. Okay, so rule number 4 states that if two chords, that is to say chord AB and chord DC, are intersecting each other at point O, then the following equality is true, that OA times OB equals to OC times OD. Okay, so we actually can implement rule number 4 in our circle, because in our circle we have chord AP that intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DP, and so according to rule number 4, AO times OB equals to DO times OB. Okay, AO times OP equals to DO times OV. And again, we have all the values of the line segments inside the circle. The only missing line segment is CP, so we can solve this equation, and we found out that the value of CP is actually equals to 16 over 13 units. Okay, the value of CP is 16 over 13 units. In the next step, we extend that line segment DC until it touches the circle at point Q. Point Q is the point of contact between the circle and chord DQ. And we found out the value of the new line segment CQ according to the fourth rule. Because in the circle we have chord AP. Chord AP intersects with chord DQ at point C. Point C is the point of intersection between chord AP and chord DQ. So according to rule number 4, AC times CP equals to DC times CQ. Okay? AC times CP equals to DC times CQ. And again, we have all the values of the line segments here, and the only missing variable is CQ. So we solved this equation, and we found out that the value of CQ equals to 16 over 3 units. Okay, and then we extended line segment BC until it touches the circle at point R. Point R is the point of contact between the circle and chord BR. And we again repeated on the same process in order to find out the value of line segment RC. We can implement rule number 4 because chord RB intersects with chord DQ at point C. Again, chord RB intersects with chord DQ at point C. Point C is the point of intersection between chord RB and chord DQ. So according to rule number 4, RC times BC equals to DC times CQ. Again, according to rule number 4, RC times BC equals to DC times CQ. And again, the only missing variable is the only missing line segment is RC. We know all the values of all the other segments, of all the other line segments here. So we put the data inside this equation. We found out that the value of RC is actually 4 units. Okay, the value of RC equals to 4 units. And then we actually found out the values of all the line segments inside this circle, and the only missing string is the radius of this circle. And we found out the value of the radius of this circle according to the fifth rule. The fifth rule states that if two chords are intersecting each other at 90 degrees, if chord AB intersects with chord DC at 90 degrees, they create 90 degrees at the point of intersection. That is to say, at point O, the point of intersection, they create 90 degrees. Then the following equality is true, that 4 times the radius squared equals to AO squared plus OB squared plus CO squared plus DO squared. Okay, so whenever you have two line segments, for example line segment AB and line segment CD, that are intersecting each other